The fire inspector should take a lead role in the improvement of local water resources. This role is not explicitly stated in the fire code, but is implied in the task that a fire inspector must perform every day. Adequate and reliable water is a community's best fire protection. Although many types of fire suppression agents exist today, water will always be the predominant agent used in firefighting. It is plentiful, inexpensive, easy to store, and is stable and does not react with many chemicals. It can absorb great quantities of heat through vaporization when suppressing fires. Inspectors must work with other local government and utility officials to review water supplies, identify system deficiencies, and ensure system improvements. Learning objective number 1. Identify and describe the water sources in your community. Water system components require maintenance by water utilities or fire departments. Emergency secondary supplies should be identified. Additional water sources may be vital in emergency situations. Fire departments must always be prepared to convert their method of operation to other available sources of water in an emergency. Emergencies may include floods, broken water mains, failed pumps, frozen valves, earthquakes, and other types of service interruptions on the system. An emergency water contingency plan should be part of every fire department's emergency planning process. It is usually addressed through the Fire Prevention Bureau. Two general types of utility systems: gravity feed water systems and direct pump pressure water systems. The utility infrastructure includes water sources, filtration systems, distribution systems and storage systems, water towers, mains, pumps, chlorination plants, and fire hydrants. Utilities are normally publicly owned and operated through fees and tax collectors. Urban water supply systems include fire hydrants. The fire inspector should make recommendations on the location and spacing of hydrants based on standard like the American Water Works Association. In urban areas, recommended hydrant spacing is 500 feet in residential neighborhoods and 300 feet in industrial and commercial areas. Tanks should be pre-planned by fire departments so that they are aware of all the hazards that may be present, including electrical hazards and confined spaces. Rooftop tanks are typically installed inside the building, or they may be mounted at rooftop to provide 15 psi pressure at the topmost sprinkler head. Water sources on private property may be required for public protection, and legal agreements should be established. The fire department needs legal right of entry, although the FD can have the right to enter properties that are on fire. The fire inspector, as water supply officer, should establish the formal agreements with any private water source that may be required for community fire protection. Streams may be usable water sources, and the water supply officer must be able to determine the fire flow of the water source for both total capacity and flow in gallons per minute. They must be capable of delivering water in drought conditions and must be accessible to the fire department. With limited water supply, the fire department may need to shuttle water with tenders. ISO requires arrival in 15 minutes of initial fire department water flow, and the delivery rate is specified by NFPA 1142. Automatic and mutual aid fire departments under both NFPA 1142 and the ISO rating system are required to establish minimum automatic aid or mutual aid agreements to verify the capability to deliver water using a tanker shuttle system. Learning objective number 2. Evaluate the importance of the water supply systems. Adequate and reliable water systems are a community's best fire protection, and although many types of fire suppression agents exist, water will always be the predominant agent used in fighting fire. A complete survey of the jurisdiction determines the minimum amount of water that must be available to control fires based on specific risk according to the property's hazard classification, occupancy, use, and type of construction, and exposed buildings located within 50 feet of the structure requiring a fire flow. NFPA 1142 classifies buildings numerically from 3 to 7. The construction classification is based on the 5 major construction types. The higher the number, the greater the fire risk. The construction classification, along with the hazard class and the potential exposures, are used in NFPA 1142, the standard on water supplies for suburban and rural firefighting, to determine the fire flow for buildings. The NFPA 1142 calculation also examines exposure structures. Exposure hazards are any structure more than 100 square feet within 50 feet of the building under consideration. High occupancy hazard class buildings rated 3 or 4 are also considered exposures if they are within 50 feet of the building, regardless of size. Minimum amounts of water for any exposure shall not be less than 3,000 gallons. Exposed buildings over 100 square feet must be considered for an additional water supply. Since radiant heat may travel 50 feet or more, Exposure required for an additional water supply increased 50% over the amount needed for the evaluated structure. As said, the construction classification, the hazard class, and the potential exposures are used to determine the fire flow for buildings. The minimum water supply is calculated by determining the volume of the structure, then dividing it by the hazard classification number. The result will be multiplied by the construction classification number, and if any exposure factor, if the exposure exists within 50 feet. Learning objective number 3. Recognize specific requirements of the ISO grading for water supply systems. Waterworks were developed to provide a distribution system for domestic water and sanitation purposes. The side benefit was to provide water for fire suppression. Engineers in the early 1900s analyzed the use of waterworks for fire suppression and began to develop standards on water main sizes and capacity, as well as estimates on how many fire hose streams might be needed to suppress a large fire. They believed that, in a rough way, the number of hose streams was related to population size. The ISO generally determines the Public Protection Classification, PPC, for most communities on a 10-year basis. The classification of the community affects the fire insurance rates charged by any insurance provider to residents or businesses. Community fire defenses for fire insurance purposes are measured by the ISO Public Protection Classification Schedule. The Insurance Service Organization is an independent source for information on property and casualty insurance data. The ISO grades and maintains data on community fire defenses that are used to establish fire insurance rates based on risk. The ISO requirements are minimally based on water delivery to a fire scene at a rate of at least 250 GPM for at least 2 hours. Insurance companies use this information in establishing fire insurance rates that the homeowner or business will pay in their premiums. ISO rates community fire defenses by Class 1 through 10, with Class 1 being the best rating and Class 10 being considered unprotected. The classes are based on evaluation of the community's fire department, fire alarm communication center, and water distribution systems. The ISO uses the fire suppression rating schedule to determine the public protection class. The water delivery system is evaluated for public works capacity, water main capacity, and distribution of fire hydrants on the system. The ISO determines the test locations by identifying buildings requiring a minimum fire flow of 3,500 GPM. The buildings protected by automatic sprinkler systems fall under the commercial rating schedule. The water supply is credited based on the total flow in gallons per minute at 20 psi residual pressure at the test location for a specific duration of time. The lowest rate of flow is used for determining the credits to be issued under the water supply and are based on the following criteria. 1. The needed fire flow in GPM at the test location. 2. The capacity of the supply system in GPM. 3. The capacity of the water distribution system in GPM. And 4. The capacity and delivery of water from a fire hydrant within 1,000 feet of the property at the test location. Learning objective number 4. List the responsibilities of the water supply officer. The water supply officer manages and documents all available water resources within the jurisdiction. Because inspectors are familiar with the community, the types of building construction, the types of fire protection systems, and unusual hazards in the buildings, the WSO should work closely with the Fire Prevention Bureau. The water supply officer is critical during emergencies, but even more so during the planning and permitting phase of fire prevention and inspection. They are responsible for systems and source data, determining capacity, developing maps and card systems, and conducting inspections. Rural areas seldom have a well-developed infrastructure for distribution of water, and generally each home may have its own well for domestic water supply. Rural fire departments must develop water resources from a combination of natural water supplies such as lakes and ponds, and hauling water with fire apparatus in the form of tankers and water tenders. The natural sources of water may include creeks, streams, ponds, lakes, wells, pools, tanks, cisterns, and rivers. NFPA 1142 governs the application, development, and use of natural and man-made water sources for rural firefighting purposes. Learning objective number 5. Explain how to conduct a flow test. Water supplies must be adequate and reliable. Proper design and operation of automatic sprinkler systems depends on system flow and pressures. This water flow information is also important to the fire department for the purposes of firefighting capability within a given area. Conducting fire flow tests is especially necessary in older portions of towns and cities that may have underground supply piping that is centuries old. A complete understanding of the water supply distribution system improves firefighting strategies and helps the fire department overcome any deficiencies that they identify in the water system. Fire inspectors should obtain water maps of the local utilities that identify the size and connections of the underground water mains. The flow test procedure is outlined in NFPA 291, recommended practice for fire flow testing and marking of hydrants, and should be followed by the fire inspector. Preparation is key to proper testing. You should always notify the utility and the community. Avoid peak demand times so that the public is not inconvenienced with brown water or low pressures. You should review utility maps to determine surrounding water main sizes. In gridded systems, water will always flow from larger water mains to smaller water mains, and when choosing the flow and test hydrant, the inspector should determine the flow direction to establish the test fire hydrant closest to the construction site. Residual test hydrants should be in the direction of the water flow, and in some cases only one fire hydrant may be available and will have to serve as both the flow and residual test hydrant. Fire inspectors must have the proper tools and equipment to conduct a flow test. You need a 6-inch ruler marked in 1/16 inch increments for measuring the hydrant outlet openings and to draw the water supply curve on the special graph paper. A clipboard, pencils, and forms are required to record the test information. A 2.5 inch tapped hydrant cap with water pressure gauge that reads up to 250 psi. The water pressure gauge determines the static and residual pressures on the water system. A pitot test gauge or diffuser measures the velocity flow, and you'll need a hydrant spanner wrench and possibly a 90-degree elbow or a play pipe with a smooth-bore nozzle. Fire hydrants usually have one of the 3 outlet configurations. The outlet type determines the proper coefficient of discharge for the fire hydrant flow calculation. Open the hydrant's 2.5 inch outlets and stick a finger inside to feel the outlet's edge inside the barrel. A smooth rounded inner edge means using 0.9 coefficient in the calculation equation. A sharp square edge will use a 0.8 coefficient. A lip that projects into the barrel will use a 0.7 coefficient. Measure the inside diameter of the outlet using a 1/16 inch ruler. It's important to make sure you properly measure the outlet diameter, as a 1/16 of an inch may cause a 5% error in the flow calculation. Avoid using the 4.5 inch steamer connection, as this does not produce a solid flow like the smaller 2.5 inch outlets and will affect the accuracy of the flow measurements. The following is the flow test procedure. 1. Install the hydrant cap pressure gauge on the flow hydrant outlet. 2. Slowly open the hydrant fully and record the static pressure on the pressure gauge. This is static pressure or water at rest. Remove the hydrant cap pressure gauge and relocate it to the residual test hydrant upstream of the flow test. If only one hydrant is available, leave the gauge on the flow hydrant and test using the other 2.5 inch outlet. 3. Open the hydrant fully and let any debris from the water main flush out. 4. Once the water is flowing clear, take the pitot gauge reading. The pitot gauge should be firmly held and inserted into the flowing water at the center line of the outlet and at least half the diameter of the outlet away from the barrel. Once the gauge is properly inserted the correct distance from the flow, take the pressure reading on the pitot gauge and record it. 5. While the water is still flowing, record the pressure decrease on the hydrant cap gauge downstream on the residual test hydrant. This records the remaining pressure on the system and should drop the static pressure by at least 25% or 15 psi to validate the flow data. If the flow has not decreased the static pressure by 25% or 15 psi, open an additional fire hydrant outlet until you get a sufficient drop in pressure. If additional fire hydrant outlets are used, record the pitot reading and the residual pressure on the test hydrant at the same time. Take the data collected and draw the water curve from the hydrant system on the graph paper. The graph will show the available water at the fire hydrant location. Water graph paper allows the water curve to be drawn as a straight line. Any point along the line will show the pressure on the left and the flow in GPM at the bottom of the scale. First, plot the static pressure at zero flow, which represents the system's available water. Next, select the scale on the graph paper and locate the flow pressure at 15 psi with a total flow of 654 gallons per minute. The water curve can now be drawn on the graph paper using the ruler to connect the 2 data points. This special graph paper allows a curve to be drawn as a straight line, and the area located below the line represents all the available water from this fire hydrant. As you can see in this figure, The maximum flow for this hydrant is 654 gallons per minute at 20 psi residual pressure. Freeman's formula is used to calculate the flow based on the data you recorded in the flow test. 2.983 is the standard factor, C is the coefficient of the outlet that you measured with your finger, D is the diameter of the outlet, you're going to square that, and P is the pressure, and you're going to find the square root. In this particular example, the measurement of your pitot gauge was 15 psi, and that goes here, that's your pressure. The outlet had a 0.9 coefficient, which was a smooth inner edge, and the diameter was 2.5 inches. 2.5 inches squared is 6.25. The square root of 15 is 3.874. If you measure 29.83 times 0.9 times 6.25 times 3.874, you come up with 654 gallons per minute, or close to that because this square root is rounded off. And in summary, your water supply sources include fire hydrants, elevated storage tanks, pressurized tanks, rooftop tanks, private water sources, streams, water tindals, shuttles, and mutual aid. The importance of the water supply system is that the adequate and reliable water system is the community's best fire protection. You need a complete survey of the jurisdiction to determine the minimum amount of water that must be available to control fires based on specific risks according to a property's hazard classification, occupancy use, and type of construction, with exposed buildings located within 50 feet of the structure. NFPA 1142, standard classifications buildings numerically from 3 to 7. The ISO grades and maintains data on community fire defenses to establish fire insurance rates based on risk. The ISO requirements are minimally based on water delivery to the fire scene at a rate of at least 250 GPM for at least 2 hours. Insurance companies use this information in establishing fire insurance rates, and the ISO rates community fire defenses from classes 1 to 10, class 1 being the best, class 10 is basically none. The water supply officer is responsible for system and source data, determining capacity, developing maps and a card system, and conducting inspections. A flow test is important because water flow information is necessary to determine strategies for fire protection and to make sure that you have enough water for the sprinkler system. To conduct a proper flow test, you need to have the proper tools. The outlet type determines the proper coefficient of discharge. The outlet cap pressure gauge goes on the flow hydrant first to record the static pressure. Then you relocate the cap gauge on the residual test hydrant to make sure you have at least a 25% or 15 psi drop in pressure to validate your test. Then you flush the hydrant. You take a pitot gauge reading, and then you record the decrease on the residual test hydrant. You draw the curve on hydraulic graph paper, and you use Freeman's formula, which is Q equals 29.83 times the coefficient times the diameter squared times the square root of P. Be on the lookout for Chapter 14.